Welcome to this FMSP online revision video for the MEI Differential Equations module, or the DE module. This video is going to cover the numerical methods topics that are mentioned in the specification, and that's specifically things like tangent fields, or slope fields as some people refer to them, and using a method of solution called Euler's method, which is an incredibly useful application for differential equations which you can't solve analytically, or even if you can. This is what the specification says about the numerical methods in the course. Let me highlight a few things for you. It mentions these tangent fields here. That only requires you to know about tangent fields for first order differential equations, but you do need to be able to interpret them, whatever that means. They mention that changing values of coefficients in the equation, you should recognize what effect that has on this tangent field, whatever it is. These things are useful because you can sketch them relatively quickly, and you can also find the solution curve for a differential equation from the tangent field. So they're asking you to recognise that. And then there's another mysterious word about tangent fields, these isoclines. You need to know what they are, and I will tell you shortly. And you can use them to sketch a tangent field and then a solution. And sometimes they're really helpful to understand what the solution behaviour is like. So those are the things that they mention about tangent fields, and slightly differently, a different emphasis. This is actually on solving differential equations. Now, if you can't solve them by any other method from the rest of the course, you can use something called Euler's method, and so that's what it's talking about down here. They call these step-by-step methods. They only discuss one in this course, which is Euler's method, and actually they don't say very much about it, but they say you need to be able to use step-by-step methods. For example, Euler's method to solve first-order differential equations. Notice first-order. They could use simultaneous equations where appropriate, but all of these things, which sound a little bit scary because it's quite vague, are covered by this under here, which says adequate guidance will be given in examination questions, i.e. they'll give you specifics, so they'll tell you what to do. Generally, when I've seen them ask about it, they will use Euler's method, which is the one we're going to look at, but they may do a slight variation on Euler's method, and that, according to the specification, would be fine. They're allowed to do that. If you understand the principle of Euler's method, you will almost certainly understand the principle of any method they do show you in the exam, and they'll talk you through how to use it. So that's the background. Let's do a very quick introduction to those two bits. And the best way to do that is to see something moving, even though you can't do this in the exam. I'm going to use a program called GeoGebra to show you what's going on with these tangent fields. So on the screen at the moment I have a coordinate grid, and I have a spreadsheet I'm going to use for Euler's method later on, a couple of sliders, and there's a differential equation saying dy by dx is equal to y. Now you can solve that differential equation using separating the variables, and I'm sure you could do that, and if you can't, go and look at the video on first order differential equations. The point is, you need to know what a tangent field for this differential equation would look like. And actually, it's not too hard. If I just pick a random point on the screen, let me get my pen going here. If I pick the point 1, 1, for example, and drew a blob there, what I could do is realise that has the x-coordinate equal to 1, and the y-coordinate equal to 1, and putting those numbers into the differential equation. In this case, all I need is the y value equal to 1, realising the gradient is 1 at that point. And I could draw a little line indicating that the gradient is that sort of slope at that point. If I pick a different point, for example the point up here, which is the point 0, 2, if I put the coordinates into the equation here, again all I need in this case is the y value, which is 2, I'd realise the gradient is a bit steeper here, it's a gradient of 2. I could do that for every point on the plane. This is dull. In the exam they do expect you to know that's what you need to do, but they won't ask you to do thousands of these things. This is crying out for a computer, and we can ask a computer to do this very easily. So if you did it for lots of points on the plane, you would see a whole bunch of little lines that would look like this. So this is called the tangent field for our differential equation. I'm using GeoGebra. You can always get a differential equation tangent field by typing in slope field, and you can see the options there. You've just put the function in, which is what dy by dx equals, in for f there, which is what I've done, and it will plot the tangent field for you. Obviously you can't use this in the exam, but it's helpful to be able to see what it should look like quickly. I'm just going to get rid of my horrible text here. You can drag the screen around and you can see the lines are all changing nicely. They look a bit like iron filings pointing in the right direction. Notice none of these are curves, but from the tangent field I could draw a curve. If I put a dot anywhere on the screen, say here, I can sort of join the dots and realise the curve must do something like that to follow the line. If I have a dot up here, then it would go something up like that. And actually I can check with GeoGebra, it can solve differential equations in some cases. I'm going to ask it to solve it from this point here, and that's what this line is doing. You see these are the various solutions. And they're all loads of different solutions because you get a constant of integration when you solve a differential equation. So all of these are possible, and you can see that my guesses are approximately right if I go through any points on my curve. This is doing it with a computer. Obviously, doing it by hand is less accurate, but it does give you a really good way of seeing what sort of solution you're likely to get. There's one other thing that they mention, which is this idea of isoclines. Which are a posh word for things that are the same. You've probably heard of other words that sound like they have the word iso in it, like isobars. You may have seen them on weather maps. Isometric means same measure. Isobar means same pressure, because bar is a measure of pressure. So in our case, isocline means same cline, and you probably eventually will recognise the word cline from the word inclination. So cline is to do with slope, incline if you like. So if you're talking about isoclines, you're talking about same slopes. And let me show you what these isoclines look like. Again, I'm just going to get rid of my annoying lines on the screen. I'm going to turn off the slope field as well. The isoclines look like this. In my case, they are horizontal lines, and I can see all of these things are isoclines. Let me just convince you, this is the sort of thing you'd work on. The isoclines are where the gradient is a constant. So in our case, it's where dy by dx equals some constant k. And looking at the equation, that is equivalent to saying y equals k. And you recognize that, I hope, as a straight line. In fact, it is precisely these straight lines that are moving up and down. A different differential equation will give you different isoclines. It is really important that you recognize these things are not the solution curves. What they do, though, is give you a way of sketching the tangent field easily, because if, for example, I set k to be 1, let me just drag it to 1, then I'd know that everywhere on that line the gradient is 1, and I could draw a whole bunch of little lines at 1 along here. So it's a way of being able to quickly sketch in a whole bunch of lines on your tangent field. If I turn the tangent field back on, you'll see that those match roughly with what's going on. And you can also see, as I change the k value, that every line this goes through is where the gradient is the same all along that line. So these isoclines, you need to know what they are, you need to know why they're useful, but you just need to know really what tangent fields are and how isoclines help you sketch them. While we're on this, I'll show you a couple of other versions. Perhaps if I turn the tangent field off, I'm just going to change the differential equation. Let's do x plus y this time, or y plus x. So I'm going to turn the isoclines off here. You probably saw it, but if you were going to draw the tangent field straight off, it ends up looking like this, which is possibly a surprise. It doesn't look quite so simple. But if you didn't know that, what you could do is pick a value, find out what the isoclines look like. And if I show you what that looks like, it's actually relatively easy. dy by dx would have to be a constant, so you could always start with that sort of line, and then realise that dy by dx is the same as y plus x. So rewrite it as y plus x equals k. Turn that into something you recognise. In this case, it's going to be minus x plus k. And I think that's pretty straightforwardly a straight line with a gradient of minus 1 going through some y-intercept of k. And lo and behold, it is that. So all these are the isoclines. If I set k to be 1 again, I would know that everything on this line has a gradient of 1, so I could draw lots of little lines like this. If I set k to be 0, I could draw lots of little lines with a 0 gradient. They'd have to be like this. And eventually you'd begin to fill in the blanks, and eventually you'd create a tangent field which does capture this sort of behaviour. The solutions look like this, by the way. It's important you recognise the sort of flavour that the tangent field is actually like sketching a family of solutions. So if you plotted all possible solutions to a differential equation, you'd essentially get a filled-in tangent field. So this is the sort of thing I mean. These are all solutions that could be possible out of this differential equation, depending on the constant of integration. And the sort of the flavour you get is captured by the slope field with a slightly less confusing mess on the screen than if you were trying to draw these hundreds of curves. That's why tangent fields are useful. I'll show you how to use them in the exam question, but it's important that you realise you don't really ever want to do them by hand, except in the exam when you're just proving you know what they do. So, that was my introduction to tangent fields. We'll quickly look at Euler's method. Euler's method is Also very important. Again, it's because it's a numerical method, it feels a bit fiddly to have to do it by hand. This is really designed so you can number crunch stuff on a computer quickly. As ever in the exam, you have to do it by hand to show you know what's going on. One day will be in the world where you can take your exams and show you could use this on a computer. But it is good to slow it down to a step-by-step to see what's going on. Here's the basic idea. When you solve a differential equation, you get an answer which is a function. So quite often you have a differential equation which is dy by dx equals some function which may have x and y in it. But when you solve it, you want y equals something to do with x. Maybe you call this function g. It's a different function from what you started with. But you're trying to get this function which you could plot on a curve, and quite often they ask you to draw what these things look like. So that was all just a little sketchy version. But the point is, if you can't get the curve exactly, if you could get a list of points which are on the curve, or at least close to the curve, then you would be pretty good. We're pretty close to a solution. So the big idea, remembering that an answer to a differential equation is a function, and so a good approximation would be a list of points. And that's the basic idea you need to remember. A list of points, so maybe points that would lie along this curve in this shape. Even if they're slightly off it, a good approximation may be all you need. So the big idea is that if you have a point on the screen, let's say I put a point here, we're on some sort of coordinate, but I'm not going to put any numbers on. If I have a point there, where would the next point be? Because if I can figure out what the next point would roughly be, then I could repeat this process in a step-by-step way, which is a clue to why they call these step-by-step methods. So what is the next point? Well, first of all, I'm going to go along a bit to the right. I'm going to jump to the right, and I'm going to call this a distance h. It's quite often common in mathsy things that they call this a height, which is a shame, because it's not really what we used to think of as a height, because it's going sideways, but maybe you remember this sort of thing from the trapezium rule, which is also a numerical method, but that one's for integration. This is a numerical method of solving differential equations, and I'm trying to get the next point on the curve, but I don't know where it should be. If I go along a bit to the right, then either the point is up here somewhere, or it's down here somewhere, or it's maybe roughly the same height. But somewhere on this line will be a point, the next point on the curve. But I usually have some information. I can't tell exactly where the point is, but they quite often tell me, because it's a differential equation, they tell me what the gradient is at any point. So what I could say is, if I know the coordinates of this point, let's call it x0, y0, I could make a pretty good guess that the gradient at that point, in fact I know the gradient at that point, is exactly what happens if I put that into this function. And that's what we were using for the tangent field. So let's say the gradient turns out to look a little bit like this. Now, if the gradient didn't change at all by the time I get to this line, then the gradient would still be that. So I could sort of extend this line over to there, and then I'm going to guess that my next point is precisely there. Or rather, not precisely there, because the chances are the gradient has changed very slightly before it gets there, and so maybe this is slightly out. But if I wanted to be less out, what I'd do is decrease the step size here, maybe only go half this distance, and then I could guess that the point should be there. The point I'm trying to make is that given a point, you can pretty much guess where the next point is going to be if you know the gradient. If the gradient ends up being negative, you know the point is not going to be up here somewhere, because it's going to go down here somewhere, and maybe the next point is there, if you jump forward a little bit. So we're talking about guessing where the next point is based on the gradient at the previous point. And the big idea is the smaller the step size, the likelihood is that you're going to be more accurate. But obviously you'll get less points for a certain distance. If you need to get all the way over here, doing it in 1,000 steps might be practical, but doing it in 10 might be fine. So you need to have your step size big enough to get where you need to get to, but small enough to be accurate. Let's put this into a little bit more technical language. For a differential equation, they will give you a differential equation, I hope, otherwise you're going to struggle. And they'll give you a starting point. And to get the next point then, let's draw a little slightly better diagram. If this is the point xn, yn, I'm going general, instead of x0, y0, which is kind of like a starting point. This is just some general point. The next point, if you go along a distance of h, and let's assume it's going up. We'll assume the gradient's positive. Obviously, it doesn't have to be. What I need to know is the coordinates of that new point. So let's call this xn plus 1, yn plus 1. And obviously, I think the x-coordinate is the old x-coordinate plus h. I hope that makes sense. So we can get what xn plus 1 is. It is the old coordinate xn plus h. That's just saying you go along to the next x-coordinate and it's the step size, which is h, along. The crucial thing is, what is the new y coordinate? And actually that's not too bad either, because we generally know the gradient. We know that dy by dx, it says it at the top here, is this function, f of the point. Now, if the step size was 1, the whole point of a gradient is if you go along 1, you go up the amount or down the amount that the gradient is. So actually all I need to do is scale it by h. I'm going to claim that this length here, the side of the triangle, is precisely h times the gradient. And go and have a think about that if you don't believe it. If h was 1, it would just be the gradient. It's the amount you go up for every one along or down. But actually that gradient is f. So it's h times f. And let me put that in more formal language then. The y n plus 1 is it's whatever the old y coordinate was, because we're starting here, and it goes up by an amount which is h times f. And it's f calculated at the old point. And I think this is a good example of a scary looking maths formula that is actually incredibly simple if you understand the notation. The new x coordinate is just step size along from the old x coordinate, and the new y coordinate is the old y coordinate with a bit added on, which is the step size times the gradient. And that's all we do. In fact, this is the summary they put in the textbook for Euler's method. You get a point and you get to the next one by guessing that you go along a bit and you must go up or down a bit that's dependent on the gradient, multiplied by the step size. The other idea is that as h gets smaller, this is better. And you need to see what's going on here. So this is a really important thing, I think, to play with on a spreadsheet again. And GeoGebra is a good way to do that. So let me just show you how this works. GeoGebra has a built-in spreadsheet. You can see up here I've got a slider for my step size, which I'll just leave at 1/2 for now, so it's predictable. And what I'm doing is I'm tracking the coordinates of this point A here. You can see I'm just doing x of A, and that's the GeoGebra requirement for get the x coordinate, and this is y of A. And I'm also calculating the gradient at that point by doing f of A, because the f function is my gradient function, and this is the same one we looked at earlier in the video. I'm also calculating the point here, just from these two, so I can plot that, and this is going to appear on the screen when we're ready. So to get the next point, it's going to be the old point. Remember from the previous thing, it's going to be the old point, which is A2, if I click on that, plus h. And GeoGebra understands h is a thing I could slide around up here. So that's the next x point. The next y point is going to be the old y point, which is this number, plus h times the gradient at the old point, which is this number here. In the exam it's like f of these two things. And that's it, there's the new y point. And this thing is just going to be f of that point and that point, those two numbers. And that's the new gradient. And let's just copy the idea that I want that point to exist. Okay. And you see it's created a new point. And what's more, this point moves around depending on where I'm starting. But a step-by-step method is rarely used just for one step, so let's actually realise the power of a spreadsheet by seeing what happens as we increase this. And now I've got the formulas in here, I can just copy this down. So I'm just going to copy this down, and we'll see what happens. Boom, we have loads of steps. And as I move A around, you can see that we're getting shapes out of this, and these shapes are probably roughly the solution shapes. If I put the actual solution on, you can see it's not quite following that. And if you put the slope field on, you can see that my dots are sort of overshooting the mark a little bit. But the whole point of doing this on GeoGebra is I can change the step size, and you can see changing the step size is changing how far each point is jumping along, and as I decrease h, I think we're going to get better solutions. You can see that I've run out of points though if I make h really small, because it's not getting very far each time. But now if I put the solution on, you can see this is much closer to the actual solution. And if I stop this making a mess on the screen, you can see that it does track the solution pretty well, and I'm getting a list of points which follows the solution curve wherever I start, which is pretty neat. And if h is tiny, I don't get very far, but you can see this is really quite good at tracking the solution curve. What's great is actually even GeoGebra fails sometimes to solve differential equations, so this line might not exist. Maybe there's no way of solving it, but you can still use Euler's method to get the rough shape of the curve. There are some problems. If I put a particularly problematic graph on like this one, I'm going to put y squared plus x squared. It's not that problematic, but it's quite entertaining. We might have a problem, because actually GeoGebra struggles to find this. You can see it's got a question mark here. The method it's using is actually another numerical method and it's failing, but Euler's method is still working, and you can see what roughly shapes the curves are. Notice also this, the point about numerical methods is that a slope field is still easy enough to draw, and that's the slope field of this thing, and you can see that the Euler's method dots are roughly following the tangent field quite nicely. So that's the point of Euler's method. You need to do it by hand, and we'll look at the exam questions, but you just need to recognise that you go along a bit and you go up or down a certain amount depending on the gradient. That's Euler's method. Okay, let's have a look at what this feels like to do in an exam, which, as I've said already, does feel slightly painful sometimes. It's pretty satisfying though. The examiners are aware this is annoying to do by hand, but they do need to check that you know, as I've said before, that you know what's going on. So here is question 2 from January 2010. I've actually looked at part A in a different video where we were looking at solving first order differential equations, so I'm going to look at part B, which gives you a slightly different differential equation. They've put the y squared in here. This is now a non-linear first order differential equation, and all sorts of methods which you used to be able to use are now unavailable. In fact, you can still separate the variables, I believe, here, but we're not going to do that because it ends up being hard to integrate even if you have a method for it. And they don't ask you to do that, they ask you to solve it approximately using a tangent field and then by Euler's method. So we're going to see both of them. In fact, the tangent field bit is extremely easy, 4 marks available for this, but they give you the tangent field on a little insert. So I've copied that here, which is quite useful, and they ask you to sketch the solution curves through the origin and through 0, 1. That's this bit here. 2 marks for each, believe it or not. It's quite nice actually, because they've realised that the painful bit is drawing the tangent field. This is what something a computer should do, and they've got a computer to do it for you. But then interpreting it, saying how do these solution curves work, is what they're checking you understand. And it's not hard. So if you mark the origin on here, which I'm going to do in red, the solution curve must be at that point, it looks like all the vertical y-axis has a flat thing, so the solution curve must be flat at this point. And if I just kind of join the dots carefully, they expect you to be pretty accurate here. You can see it must be heading up somewhere like this, and it looks like it's pretty much vertical here, and it looks like it's going to be symmetrical on the other side. So I think the solution curve will be something like this. They're not going to get really picky. This is a sketch, not a plot, and there's no way you can plot it without having the solution, but the tangent field suggests the solution would look something like that, which is a relief because it's relatively easy to do. If I do the other one in a blue, a different curve could go through 0, 1, so if I mark that point on here, a similar thing is going to happen, but it looks like it's getting steeper, quicker. Maybe that's an illusion, but it would be something like this from what we can see. And I think if your curves look something like that, you would get 4 marks, which is quite nice because that feels like a relatively easy 4 marks. I hope it feels doable to you. Let's have a look at the other bit of the question though, because that's the only tangent field they ask on this bit. The more involved bit is the Euler's method. And you can see what I mentioned earlier, that they tell you what to do here, so hopefully you can recognise these two formulae. They've used R instead of N from my example. They've given us a starting point, but they're telling us to get the next x one you go along h, and to get the next y one you go from the old one, you go up h times the gradient of the old one. And to do this by hand in the exam, you need to draw yourself a table, and the examiners will expect you to do this, and they need to see enough working to show that you know what's going on. So don't be afraid of writing down lots of details here. So I would have a table with x values and y values, and probably y dashed values, gradients at that point. You may want to have more columns in your table for h, but h is not going to change. They've told us that h is 0.1. So make sure you've noted that. And they've also given us the answer. We're expecting to get 1.0201 by using Euler's method with 2 steps, step length of 0.1, so we're going to end up at 0.2. Obviously we're starting at 0 on x. So my first thing to write down is the starting point. X is 0, y is 1. And the gradient, well, if you check back at the differential equation, it looks like this thing. So there is a little bit of work to do here. If you do the rearranging, you get this. dy by dx equals tan x. I'm going to factorise it. You can see that we're going to get 1 plus y squared. So this is quite entertaining. We've got to do some careful calculations. You need a calculator at this point. To get the gradient though, what you can do is dump these two numbers into here, and actually if you put 0 into tan you will get 0. So the gradient is in fact 0 at this point. That's nice and easy. It's not always going to be that nice. We're on to the next step. The next step for x is along the step size, so that's going to be 0.1 since that's the step size, and the next y coordinate is the important bit, so this gap in here is going to be the bit we need to be careful about, and it's going to be the old y coordinate plus h, the step size, times the gradient. Since the gradient is 0, this is rather easy. This is just 1 still. Now this is not a mistake, because we estimated the gradient to be 0 at the first point. We are assuming along that step that the gradient is remaining the same. It's obviously not going to stay the same, but this is an approximation thing. What we now need to do is get the new gradient though, and we keep going. You see, all we need to do is get to the next line here. We're aiming for this as our final answer, and we at least know roughly what it should look like. But we need the gradient at the new point. So at this point you'd reach for your calculator, which I've got ready on the screen here. Let's do this. I'm going to get the gradient from these two numbers, so I'm going to do something. I'm actually going to make a mistake. I want you to watch what goes wrong here. Tan of 0.1, that's the x value, multiplied by 1 plus y squared, which is 1 squared in this case. And I'm going to press equals. And that's surprisingly small, and I was feeling a little worried when this first happened, and I had to think quite hard about what's going on. I wasn't all that worried because I didn't know what the answer should be, but that's 0.003, and I'm thinking I'm not going to get up high enough to get to the answer they're expecting. And I hope you realise what mistake I've made. What I've done is I've left my calculator in its default mode, and I should have checked it is in radians, which it was not. If you're working in differential equations, in fact if you're doing any calculus on any trigonometry, everybody must assume we're working in radians because it doesn't work in degrees. Sine does not differentiate to cosine if you work in degrees. We need to be working in radians, so make sure your calculator is in radians. And now if I do this, you can see I get a different answer, and it's actually looking more promising. You can possibly see why it's looking more promising, but let me write it down. It's 0.200669. 0.200669. I think it was a 3. I'm actually going to write down everything I can see, and that's useful because it shows that you know the examiner. No, you can show the examiner you know that you need to be accurate about this. We're trying to be approximate, so we don't need to introduce rounding errors. And if you use that to create the next y coordinate here, you'd do the old y coordinate, which is 1 plus h, which is 0.1 times this number here. If you do that, we're going to get 1.0200669 which is approximately 1.0201 to 4 decimal places. And that's a relief because that's what they asked for. And that's the meat of showing the examiner that you know how to use Euler's method. It is a pain to do it by hand. This one is actually relatively simple because there's at least one easy step you don't even need a calculator for. A couple of things you need to sort out here though, because we've done the 5 mark bit, but there are 2 other bits of interpretation. It says explain why it would be inappropriate to extend this numerical solution as far as x equals 1.6. And this is not obvious. So let's look back at this, for example, and maybe even look further back at the original question. And notice a couple of things. In the original question, it's mentioned that mod x should be less than a half pi, but we are on part B, which is a different question. So we can't use this claim here that we should dodge that because we're on a different question here. But then maybe, why would they say that up here? And if you have looked at this graph, you realise that we pretty much are starting to go vertical, and that shouldn't be too much of a surprise if you realise that the tan graph, which if you've forgotten looks something like this, has an asymptote, and it has an asymptote at pi by 2, because the whole from 0 to 2 pi gets up to there. So expecting a gradient to be defined at pi by 2 when it's defined in terms of a tan thing is a bad idea. You should realise that pi by 2 is approximately 1.5 because it's a 3.1 divided by 2-ish. So what I'm going to point out is that this is a problem because actually we're possibly going over an asymptote. Euler's method is not going to guess well when the gradient becomes infinite. If you can imagine going along a point, and if you jump ahead a bit, if the gradient is infinite at that point, then jumping along a bit to the right is not going to get you to the next point because the next point is literally straight up. So Euler's method has a problem, as most numerical methods do, when you hit strange parts of graphs, like asymptotes. So I think referencing your graph in part 2 here, or part 3 essentially, but saying the solution would cross an asymptote, or something like that would be what you'd need to mention. And if you show that you know where the asymptote is, they're not going to then start doubting you know what you're talking about. So the asymptote happens at x equals pi over 2. I think to guarantee that you get both marks, you could probably mention that tan x has that asymptote. Just to, and if there are 2 marks, try and say 2 things. So just show that you know why that's happening. And if you're mentioning an asymptote at x equals pi by 2, and mentioning that this numerical method will fail if it crosses an asymptote, they're going to give you some marks for that. Finally, there's a 1 marker to finish, and this is quite common, and it's something you just really pray for because it's an easy 1 mark. How could the accuracy of the estimate found in part B, part 2, that's this thing we were doing, how could it be improved? Make h smaller. Because as we've been talking about, if you decrease this step size, if you say h tending to 0 makes a solution more accurate, or something like that, numerical method accurate. I say more accurate. Anything which is emphasizing that solutions generally have less error when the step size is smaller is going to get you the mark there. Okay, I'm very quickly going to look at one more question. This is from June 2011. I'm going to do this because it actually discusses tangent fields in a little bit more depth and shows you how they can actually still expect you to do some work on these instead of just drawing a little picture. This time they've given us a differential equation. There was a part A to this question which I'm completely skipping for the moment. This differential equation looks like this. It's first order. It is definitely non-linear. There's a square and a square root on the y. But maybe that looks a vaguely familiar sort of formulae. And they are asking you to solve it approximately using a tangent field. Before they ask you to sketch the tangent field, they ask you to describe the shape of the isocline for which dy by dx is 0. Not 0, sorry, 1. Immediately, I think you can dive in by saying, well, if dy by dx is 1, then actually what we've got is the square root of x squared plus y squared is 1. And you should be itching to square that, because then we're in the situation where x squared plus y squared is also equal to 1. And I think if you don't recognise that, you should not be taking this module, because this should be a familiar geometrical object. It's interesting that the solution to differential equations, though, becomes about a knowledge of geometry and pictures. And the idea that pictures of maths are important is quite a profound thing. I'll stop preaching at you, though. This shape is clearly a circle. Radius 1, centre the origin, and I would write 0, 0 for that. Please notice you need to mention these 3 things. A circle, it needs to have radius 1, and it has to have a centre, otherwise they'll probably knock a mark off. It's not a surprise that circles are turning up when you see an equation looking like this. This is kind of like the Pythagorean definition of a circle. What we also know, though, that the isocline is a circle. That means all the gradients on that circle are the same, and in fact they are 1. And that's going to be useful when we come to sketch it, which, lo and behold, we have to do in the next question. So let's draw this quickly here. Before you mark any scales on, but I'm doing this completely roughly. I'm not doing it on squared paper. And it's important that you can get the hang of sketching, just sort of to get the important concepts rather than the sort of accurate plotting. Someone once said, I should look it up really, that maths is the art of making precise statements from imprecise diagrams. And it's actually quite a profound thing too, because the idea that you can draw something sort of sketchy but reason precisely without any doubt is basically what maths is all about. So let's get an imprecise sketch here which captures the important things. We've just done the circle radius 1, centre 0, 0. Before I sketch that on, I should figure out how far my axes are going to have to go. So I'm worried about this one. If I did the same plan as I did for part 1 on this one, I would get that the square root of x squared plus y squared is 3, and suddenly x squared plus y squared is going to equal 9, and then I just have to think, well, what's that? Well, it's a circle. Radius 9? No, radius 3. And so the biggest radius I'm going to need is 3, which means I think I can justify myself in drawing the scale of 1 to 3 on each bit of my axis. It's a pretty useful skill to be able to sketch scales relatively approximately and quite quickly. So I'm now pretty convinced that all of these are going to be circles. I've done the first one. I'm just going to do it in a dotted line. And that was from part 1. So that's the isocline for the first one. put an arrow there. The second one is going to have a radius of 2. It will be x squared plus y squared equals 4, which is, as you know, having a radius of 2. And that'll look like this. And I've got a really predictable diagram turning up. These are the isoclines. They are not solution curves. What they do is they let me figure out what the gradients look like in certain places, because it does ask me to do that. It says use these isoclines to draw a tangent field. So let me change colour for this. I'm going to draw the tangent field in a bluey colour. I know everything on the first curve I drew would have to have a gradient of 1, which is precisely 45 degrees. It's quite hard to sort of force your brain to focus on getting these angles right, but think about what 45 degrees means. The next one would have to have a gradient of 2. That's the whole point of having dy by dx equals 2, and that's steeper. So let's go a steeper line here. And these do not have to be super accurate. It's very hard to just get these things exactly right. But it's got to be obviously steeper than your gradient 1 for this to sort of make sense. And the next one's going to be steeper still. It's going to be where it's 3. So let's just join that one up. That one here, so even steeper, and you can almost go vertical. I mean, it's not vertical, but the gradient of 3 is pretty steep. And as long as it's looking steeper than the previous one, I think we're going to be okay. It's quite hard, I think, to do this right, but the examiners know that this is hard to draw, and we're doing a sketch, not a precise diagram. And I think that's all you need to do. You could obviously try and fill in other bits of gradients. It would be probably always worth thinking what happens at obvious places, like this thing in the middle. Well, if you put 0, 0 into this, you're going to get a gradient of 0. So there's definitely a sort of degenerate gradient in the middle. It is 0. It is flat, right in the middle. But that's probably going to get you the 3 marks for the drawing the tangent field. You could fill in some other gaps if you wanted to, but I'm certain that they would give you the 3 marks for drawing all the little tangenty lines on the isoclines that you've done. Part 3 though says sketch a solution. We're at the stage of solving this. Notice this time we're not solving it by getting an equation, we're solving it by getting a picture of the curve. If it goes through 0, 1, let's do this in a different colour. I'll do this in a sort of vaguely orange colour. 0, 1 is here. So I've got to sort of join the dots of the curve, and it's going to go, it's pretty steep, it's going to go up like that. And it doesn't look like it levels out, so going the other way it's going to go steep down there. So I reckon that would be a good enough sketch for our curve through 0, 1. 1 mark for that. The interesting thing is that the next question is exactly the same. Sketch the solution curve through the origin, but they're giving you 2 marks for it. So your warning bells should go off, and like, what are they asking to do that's different? And this is what I've noticed earlier, that we didn't have a gradient at the origin, so unless you spotted it earlier, you'd now need to put it in. The gradient must be 0 at the origin from checking this, and that means the curve must be flat at that point. So if I do something like this, it must be flat at the origin, but it must immediately speed up and go steep, because that's what it does everywhere else. So I think that would be the curve through the origin, and you've got to make sure it looks flat. I'm a little worried that it doesn't look very flat at the origin there, so I'm just going to sort that out. And you might even want to emphasise to the examiner, if you think it's not clear, that it should be flat through the origin. So that would get you the 2 marks. And you can see that tangent fields questions, sometimes you do have to draw the tangent fields, sometimes they draw them for you. But they're relatively easy as long as you're recognising you're actually after a picture of the solution here and not anything else. So that's the end of this particular video on the numerical methods, tangent fields and Euler's methods in the MEI differential equations module. There are other videos available for other questions in the 2010-2011 papers and on the other topics. Roughly speaking, the numerical methods we've just done, the first order video, the second order video, and the simultaneous differential equations video. My name's Ben Sparks. See you on another video.